In this lesson, we're going to focus on geometric operations with vectors. So looking at these areas of addition, subtraction, multiplication with vectors, and how to devise equations or write equations with vectors. So let's say that you want to add two vectors together. If I have a vector A and a vector B, whatever they happen to look like, it's quite difficult to add them geometrically if I don't have a sense of where they're positioned. And these two vectors are free vectors. They're not actually tethered to any particular points. And so right now, figuring out how to add them together is a little bit cumbersome. In adding vectors geometrically, we use a method that's called tip to tail to help us organize the vectors to better add them together. Basically, what we do is we take the vectors and we arrange them in a certain configuration. Let's say I wanted to find the sum of the vectors a plus b based on the ones that I've drawn. What I'll do to actually ensure that I can add them together is I would reposition vector b and redraw it so that the tip of vector a, the arrowhead, is connecting with the tail end of vector b. And so once I've got them configured this way, the resultant sum, a plus b, is actually that vector that I've just drawn from the origin point of the first vector in the sum to the terminating point of the last vector in the sum. And so this works for all sorts of configurations of vectors. If I have a vector c plus a vector d plus a vector e, then the vector that goes from the beginning of C straight through to the end of the vector E is the sum of those three vectors. And so as far as adding vectors geometrically goes, that's the extent of it. As long as you arrange them tip to tail, you just have to remember, you start at the originating point of the first vector, and you end at the terminating point of the last vector in the sum, and you have your resultant vector or resultant sum. So with vector addition, something really interesting comes up if you try to do a vector a plus negative a. So if you think about what that means geometrically, a vector a has a certain magnitude and is going in one direction. But the vector negative a is a vector with the same magnitude but going in the other direction. So when you add them together, if you think about the motion that occurs here, I'd head to the right a certain distance with that first vector a, and then by adding in the negative vector, I go back to the left again, and I actually end up right where I started. So my origin point and my terminating point for the vector, the beginning and end, are in the exact same spot. And so it becomes kind of hard to actually refer to this unless we define something new here. And we actually say that the result of adding a vector with its own negative is a vector called the zero vector. It's a vector with no magnitude, because obviously it's not even a line, it's really just a point. And it also kind of has no direction to it either, because if you were to think about that vector as indicating movement somehow, you're not moving anywhere. So there's no direction to it either. The reason why the zero vector has to exist is because with vectors, we're kind of defining rules for almost a new set of numbers. So we work with natural numbers and integers and real numbers, and now vectors is kind of its own class of entity that has to have its own self-contained rules. And so two vectors can't add together to be a scalar quantity. They can't add together to be zero. So we define the zero vector is what we get when we add a vector with its negative. This also enables us to have something where I can add to a vector the zero vector, and it'll result in no change. You might feel like that's a trivial thing to have to create here, but in the bigger sense of how systems work within the broader scope of mathematics, actually having something like this is incredibly important for a set of rules to kind of be self-consistent. And so the zero vector then becomes very handy in ensuring that vector operations are self-contained. To subtract vectors, we actually have to think about the fact that subtraction and addition are two sides of the same coin. So realistically speaking, the easiest way to subtract vectors is to just add on the negative of the second vector. So if I have a vector A and a vector B that's going this way, to do subtraction geometrically, it becomes far easier to just add on the negative of that second vector and do the resultant as we would have when we were doing addition. Now, of course, that way works fairly reliably. There's another way to subtract quickly, which is known as the tail-to-tail method. So with addition, we did tip-to-tail. With subtraction, we do tail-to-tail. So what that requires is, first of all, you have your vectors A and B that you want to subtract from one another. And the way you arrange them this time is so that they're both originating at the exact same point. So now that I've arranged my vectors so that they're originating from the same point, or they're tail to tail, all I have to do to figure out the result from subtraction is draw from the tip of the second vector to the tip of the first. So the process of subtraction with vectors might not seem intuitive when you look at it. It seems kind of arbitrary. But if you actually were to take that vector B and draw the negative of it coming off of A, so that's the negative vector B that I've just drawn in there, and you were to complete addition as you normally would, going from the start of that first vector to the end of the second vector, you would actually end up with the exact same A minus B result that I got from doing the tail-to-tail method. It's in a slightly different position, but we have to remember that these are free vectors, so what's important is their magnitude and their direction, not actually the point where they're starting and ending. That's actually irrelevant in this context. So to subtract vectors really quickly, you can just arrange them tail-to-tail and draw from the second vector to the first. When we talk about scalar multiplication for a vector, what we're looking at is actually adjusting the magnitude of a vector without doing anything to impact its direction. So here I've drawn a vector A. Through the process of scalar multiplication, I might scale that up to be twice as large, and so that vector would be known as 2A. I could also multiply it by a scalar that changes its direction, which is what would make it into negative A. I could take that original vector and scale it down to half the size and write it as 1/2 A. So you can see how when I'm doing scalar multiplication, all that's happening is I'm multiplying my vector by a scalar quantity to adjust its size. It does nothing to change the direction, only the magnitude of the vector is changed. In general, if you have a scalar k and a vector A, then the result of that scalar multiplication is just a new vector, k times A. If k is greater than 0, so if it's a positive number, the magnitude changes, but the direction stays the same. If k is negative, so less than 0, then again the magnitude changes and the direction reverses. And if k is equal to 0, then the result of that scalar multiplication is actually the 0 vector. And so that's scalar multiplication in a nutshell.